Very good afternoon to all of you. Today we are going to discuss the receptors, the sensory receptors, the basic element of the sensory system from where the stimuli, that is the site where the stimulus is converted into the transduction and the translation of the impulse is converted into the then what is a receptor? We know that there are so many receptors in our body. Suppose we look at there are so many receptors present on the cell, and even we have the receptors on some of the organelle, and even we have the receptors on the nucleus. Whenever you discuss the endocrine, there are so many receptors you come across. Like that, the receptors is a structure where the sensory signals originates is called as the sensory receptors or the sense organs. The sense organs are the sensory receptors. The receptors are the non-neural specialized cells present at the afferent nerve endings. These are the non-neural tissues specialized present at the afferent nerve endings of the sensory neurons. They are capable of transforming the stimulus energy into electrical energy, which results in the transmission of the nerve impulse along the afferent nerve fibers. They transform the stimulus energy from to the electrical energy. From there, it is results into the transmission of the nerve impulse along the nerve fibers. Then what is the sensory unit? The sensory unit is nothing but the sensory neuron. It's all its ramification in the periphery and the CNS. The sensory unit. So the sensory neuron is all ramification in the periphery and the central nervous system. Then what is the receptor field of a sensory neuron? It is the part of the body of the neuron from where it samples the information. Where the information is called as the receptor. The area from where it is the sensory neuron receives the information is called as the receptive field of a sensory neuron. Then what are the different classification of the sensory receptors? The sensory receptors are classified based on the different criteria. It is divided into 5 classifications. One is you get the source of the stimulus and the type of the stimulus energy, and the type of sensation, rate of adaptation, and the clinical classification. Whenever you do the clinical examination, you do the superficial and the deep sensation. So, superficial, the deep sensation, and the other one is the visceral sensations. When you look at the source of the stimulus, some are the interoreceptors and the type of stimulus energy, the light source, mechanical, or the type of sensation, touch sensation, pressure, cold, warm, and the rate of them are slowly adapting from other rapidly adapting receptors. Suppose if you look at the classification based on the source of the stimulus, the exteroreceptors, interoreceptors, telereceptors, and the proprioreceptors. The exteroreceptors is the stimulus immediately from the external surroundings. Suppose if the receptors are the cutaneous receptors for the pain, touch, and heat and cold. Examples for the exteroreceptors immediately to the external surroundings. The interoreceptors, which is the stimulus within the body. Suppose if you look at the chemoreceptors at the bottom of the aortic arch or the baroreceptors are present in the common carotid bifurcation. So these are the aortic body. They are examples for the chemoreceptors or receptors. So the examples for the interoreceptors. Then next is the telereceptor. This is the stimuli coming from a distance. Suppose if you look at the eye or the ear, where they receive the visual receptors, the rods and cones, which is the stimulus, the light source from the distance. Even cochlea, the sound, the they also receive the stimulus from the distant source. They are called as the telereceptor. Then next is the proprioceptor. It the change in the muscle length and the tension and the movements in the proprioceptions and they plays an important role in the balance and okay. The classification based on the type of the stimulus energy. Suppose you look at the stimulus energy, the mechanical, the receptors, the mechanical receptors are present in the skin, deep tissue, they are present in the joints, they are present in the muscle and tendon, the stage receptors, the hair cells of the cochlea, the hair cells of the vestibular apparatus, the baroreceptors are the carotid and the aortic sciences. Are the examples for the mechanical the stimulus energy. Then just now we have discussed the photoreceptor of the retina, rods and cones of the light of the stimulus energy. Then the thermal, the cold and the warm receptors, which detect the change in the temperature. Then the chemical, the chemoreceptors, the example for the chemoreceptor, the taste and the smell. The aortic and carotid body receptors, which detect the levels of the arterial, the partial pressure of oxygen, the partial pressure of the carbon dioxide, and the hydrogen ion concentration. Then the chemoreceptors on the surface of the medulla detecting the level of partial pressure of the carbon dioxide. The osmotic receptors in the supraoptic nucleus of the hypothalamus, the chemoreceptors in the hypothalamus detecting the level of blood glucose of the fatty acid and amino acids of the. These are the examples for the chemical, the stimulus energy chemical. Then the extremes of mechanical, thermal, chemical energy, the receptors are the nociceptors, they detect the pain. Then the classification based on the type of sensation, the touch, cold, heat, pain, light, smell, taste. Both the general sensation and the special sensations. Then the classification based on the rate of adaptation of the receptors. Some are the slowly adapting, some are the rapidly adapting. The slowly adapted receptors are the tonic or the static receptor, which fights the action potential continuously during the stimulus application. The rapidly adapting, they also are the basic or the dynamic receptors, which fights the action potential decreasing at the rate during the stimulation. Because they are rapidly adapting the stimulus. Okay. Then the classification based on the clinical classification. The superficial receptors are present in the skin and the mucous membrane. The deep receptors are present in the muscle, tendon, and the joints, and the subcutaneous are the example of the deep receptors. The visceral receptors are present in the visceral organs.
Senses: sight, smell, taste, sound, and touch. But do you know how they actually work? How do these sense organs pick up information from the surroundings and transmit it to our brains? All of the senses have something in common: sensory receptors. Sensory receptors detect changes in the environment. We'll look at 4 of the specialized receptor cell types: mechanoreceptors, chemoreceptors, thermoreceptors, and photoreceptors. Mechanoreceptors respond to forces and movements. Chemoreceptors respond to chemical substances. Thermoreceptors respond to heat, and photoreceptors respond to light. Now let's see where these sensory receptors are put to work in our senses. Olfaction is our sense of smell. The olfactory bulbs of the brain are located on the other side of the skull bone from the nasal passage. When molecules enter our nasal passage, let's say a molecule of vanilla, the vanilla molecule will bind to an olfactory receptor in the nasal epithelium. The olfactory receptor is a type of chemoreceptor because it's activated by specific chemicals or groups of chemicals. The vanilla olfactory receptor is specific to just the vanilla molecule. Once activated, the olfactory receptor sends a signal through neurons to the olfactory bulb in the brain, and then it's sent to be processed in the olfactory cortex. Humans have about 400 different odorant receptors, which allows us to identify around 1 trillion different odors. But other animals like mice have 1,000 different receptors, and by comparison, humans don't have a very sensitive sense of smell. Aquatic animals can also smell dissolved chemicals in water, just as we smell dissolved chemicals in the air. Gustation is our sense of taste. Within the taste buds on our tongues are many gustatory receptor cells with hairs that will bind to the molecules in food and send messages to our brains. Gustatory receptors, like olfactory receptors, are another type of chemoreceptor. Our sense of sight uses rods and cones as the main sensory receptor cells. Rods and cones are located in the retina of the eye, and they're types of photoreceptors. The rods allow you to see in dim light, and the cones detect color and bright light. Our sense of hearing uses complicated structures in the ear. Beyond an almost Rube Goldberg maze of membranes and tiny bones is a snail-like region called the cochlea. Deep in the cochlea are tiny hair cells, which are mechanoreceptors that register movement that's amplified from sound waves that enter the ear. Mechanoreceptors in the semicircular canals are also used to help with our sense of balance. In the skin are many types of receptors, including Merkel cells, which are mechanoreceptors that detect touch, and thermoreceptors, which can sense hot and cold. Thanks for watching this episode of Teacher's Pet. Don't forget to like.
Then what are the different types of sensor, other sensor receptors? Suppose the epidermis, that means in here there are the free nerve endings and the mechanism this and the business corpus. You see the Japanese nerve endings and the Brazilian corpus are displayed in this. These are the law table which summarizes the tactile receptors, thermoreceptors, the nociceptors, the vein receptors, and the bronchial receptors. The tactile receptors, the business corpuscles, the hair reflexes, the mental service, and Japanese nerve ending and Brazilian corpuscles, and each and every receptors. Thermoreceptors again the warm and the cold, and vein receptors, the nociceptors. And the next, the property muscle spindle and the organs and the joint and receptors are the examples. Okay, this is the pre nerve ending and the extended tape and the pre tactile and the senior corpuscles and causes corpuscles are the causes bulb, nucleus and the Golgi tendon. These are the appropriate section function. Then the tactile receptors. Suppose if you look at the business corpuscles, the capsules surrounds the mass of dendrites in the dermis papillae. These are the mass of dendrites in the dermal papillae. The capsules surround the business corpuscles. So it carries the sensation, touch, pressure, and the slow vibration will be carried by the business corpuscles. They are more present in the fingertips. They are examples for the rapidly adaptive. The most commonly sensation that rapidly adapts the touch, and because the sensation which never adapts is the pain. Suppose the pain adapts, you will have so many problems. Okay. Then the next touch is the Merkel's disc. These are the saucer-shaped free nerve endings make the contact with the Merkel's cells in the epidermis, they carry the sensation, touch, and the pressure. They are also slowly adapting. Then the Rufinese corpuscles, these are the elongated capsules surrounds the dendrites of the deep dermis. These are the Rufinese membranes. These are the elongated capsules surround the dendrites in the deep dermis in the ligaments of the tendon. They carry the stretching of the skin will be carried to Rufinese corpuscles. They are also slowly adapting. Then the next is the Receptors corpuscles. They are the oval and layered capsule surrounding the dendrites. They present in the dermis and the subcutaneous layers and the subcutaneous joints, periosteum and some of the viscera. They carry the pressure and the fast vibrations. They are examples of the rapid erupting. Then the causes, bulbs or the causes corpuscles, they appear knotted. They appear as a knotted. They innervate the borders of the areas of the skin and the mucous membrane around the lips and the external genitalia. They are examples for the rapidly adapting. Then the tactile pain, these are the free nerve endings wrapped around the hair follicle. They detect the touch. They are also rapidly adapting. Then the free nerve endings, they are present everywhere in the skin and the many other places. They detect the touch and the pressure, the free nerve endings. Then the naked nerve endings, they are the terminal branches of the thin nerve fibers. They consist of the pain and the urostimulus. They convey both the touch and the, even along with the pain and the they convey both the touch and the temperature also. Then the nociceptors, these are the pain receptors. The physical energy that is informative at the lower and the medium moderate levels, they can be destructive at the higher intensity. The sensation of the pain it motivates us to avoid such type of stimulus. Okay? The mechanical nociceptors respond to the strong pressure, in particular to the pressure from the sharp objects. This is the type of the nociceptor. Then the thermal nociceptor, the signal either be a burning heat above the 45 degrees or unhealthy cold, very cold temperatures produce the pain. Then the chemically sensitive, the mechanically insensitive nociceptors to they respond to a variety of agents, including the Lewis key factor, the lactic acid, the potassium, adenine in the, and we discussed in the fatigue and the spectrograph. The Lewis key factor is the combination of the adenine, potassium, and the lactic. And these receptors respond to the potassium, the extremes of pH, and histamine and the bradykinin. They respond to these things. Then polymodal nociceptors, these are the single nerve ending. They are sensitive to both the combination mechanical, thermal, and the chemical. These are the polymodal nociceptors. The nociceptors axons includes both the fast A delta fibers and the slow unmyelinated C nerve fibers. The fast A delta axons mediate the sensation of the sharp and the intense pain. When it comes to the C fibers, they persist feeling of the dull and the burning pain will be carried by the C unmyelinated C nerve fibers. The nociceptors are the free nerve endings. They innervate the skin, bone, muscle, and most of the internal organs and the blood vessels and the heart. They are generally absent in the brain substance itself, although they are innervate the meninges. They are the brain tissue proper is sensitive to the pain. Nowadays, that is why there are so many people. They will do the surgery even without giving. And nowadays, they are applying. Whenever they are doing the surgeries near to the any proper areas where they have a fine movement where involved, and they will do the brain surgeries. The thermoreceptors. There are separate thermoreceptors to detect both the warm and the cold. Thermoreceptors, skin can without dysfunctioning, the temperature ranging from the 20 degrees to 40 degrees without harm or any discount does not be done. But when it comes to the brain, the function, the optimal function of the brain occurs at the 37 degrees of temperature, or the body temperature. Then the warm receptors, they begin firing, starts at the temperature of 30 degrees. The firing will increase, the rate increases up to the 44 to the 46 degrees, and after the 46 degrees, the firing rate will decrease and steeply, and the sensation of the pain begins presently mediated with the nausea receptors endings. When it comes to the cold receptors, there is a steady decrease in the whenever there is a decrease in the temperature from 24 degrees centigrade to 28 degrees centigrade, the discharge rate increases sharply. The further decrease in the temperature, there is a slight decrease in the rate of the thing, and till the 10 degrees centigrade. Below the 10 degrees centigrade, the firing level switches, and the cold itself, it acts as a very effective local anesthetic. There is no any sensation to be carried. Okay. Most of the cutaneous thermoreceptors of the free nerve endings without any obvious specification. These axons are the small and unmyelinated C fibers. When it comes to the generator potentials, the translation or the transduction of the stimulus to a receptor potential occurs at the level of the receptor. The receptor potential depends upon the activation of the cation channels, collectively termed as transient receptor potential channels. The activation of these channels, they are also called the TRP, transient receptor potential channels. The TRP channels. There are two types. One is the direct T type, another one indirect T. The direct one on the TRP channel proteins indirectly via G protein coupled receptors are the receptor potentials. The different receptors are excited by different ways. The mechanical one, because of the deformation of the receptor, the stretching of the receptor opens the ion channels. The application, when it comes to the chemical receptor, the application of the chemical to the membrane opens the ion channels. Whenever there is a change in the temperature, which changes the permeability of the membrane. The receptor potential, these channels, the cation channels, the TRP channels, the transient receptor potential channels, when it comes to the mechanical, because of the stretching, it opens, or application of the chemicals, increasing the permeability, or the change in the permeability. Whenever it is change in the temperature, it is change in the permeability of the channels will increase the receptor. When it comes to the light, the photoreceptor, whenever it causes the membrane permeability. All these cause the basic change in the membrane potential and the change in the membrane permeability of the membrane, which allows the ions to diffuse more or less rapidly through the membrane, thereby changing the transmembrane potential of a receptor. Then the generation of the impulse in the cutaneous receptor. Suppose if we look at this picture, this is representing part. These are the receptor. This is an action potential. And suppose if you remove the rings of the unmyelinated of the pacing corpus, or suppose if you apply pressure, or suppose if you cause the cutting of these unmyelinated portion, what are the things will happen? We will see in the few slides. The LPL response to the pressure, because of the suppose if you apply the pressure, the recovery will be the receptor potential of the A. And suppose if you apply the double strength, it will be the B. Suppose you apply the 3 times of then you will get the C wave, and suppose if the 4 times you will get the D wave. The strongest stimuli produce an action potential of the sensor. This is the increasing if you get the brain potential, where you produce a action potential is represented by the E. Suppose if you remove the connective tissue lamellae of the unmyelinated nerve ending in the pacing corpus, we cannot avoid the abolish the generator. Suppose if you remove these also, we will produce a action potential. The responses is, but the responses are more prolonged because of the partial loss of adaptation. Whenever the first load of Ranvier, the first load blocked by the narcotics, the generator potential is not affected, but the action potential is absent. So we will produce gets the the generator potential, we don't produce any action potential. Then if we don't doesn't generate action potential, then all the input cells are the abolished. And now the sensory in this section and the non-violent technology is allowed to generate. There is no generator potential. Suppose it won't produce any even a generator potential also. This is the receptor potential. And there is mechanical deformation. Then it will produce the action potential. The generator potential the non-violent terminal. Okay. The generator potential in turn depolarize the sensory neuron at the first mode of Ranvier. The relationship between the receptor potential and the action potential shown in this graph. Whenever there is receptor potential above the threshold level, it produces the action potential and attached to that receptor, and these action potential are conducted as a nerve impulse. Then what is sensory coding? The converting of the receptor stimulus to a recognizable separation is termed as the sensory coding. All the sensory systems codes the four elementary attributes such as the modality, the location, and the intensity, and the duration. Then what is modality? Modality is the type of energy transmitted by the stimulus. Location is the site of the body where the space where the stimulus is originating. The intensity, it is the signal by the response amplitude of the frequency of the action potential generated. The duration refers to the time to start and the end of the response to the receptor. The modality, the particular form of energy which the receptor most sensitive is called as the adequate stimulus. The adequate stimulus of the rods and bones is the light, the electromagnetic energy. The receptors, they don't respond to the form change other than the adequate. Suppose you change in the chemicals, you won't produce any response. The mechanical situation, they don't produce any response. Okay. Intensity. Suppose you can the frequency of action potential because of the temporal simulation, there will be more production of action. Or the if you put up more rhythms, like the spatial summation. This is about the frequency, increase in the frequency of the, suppose there is increase in the mechanical stimulus, will produce the more number of the action potential, both the temporal summation and the spatial summation. The different gradation of intensity can be transmitted either by increasing the number of parallel fibers or by sending the more action potential. The number of parallel fibers is the spatial summation. The number of increasing the action potential is the temporal summation. The two mechanisms are the spatial summation and the temporal summation. The spatial summation, suppose there is increase in the strong signal, there will be more number of fibers are because of this. The weak stimulus is a moderate stimulus, the strong stimulus, there will be more number of activation of the spatial summation. The temporal summation, there is increase in by the increase in the frequency of the nerve impulse by increasing the more number of increase in the action potential. This is the temporal summation. Then the duration, the receptor of the stimulus of constant strength is applied to the receptor. The frequency action potential in the sensory nerve decline to overlap. This is the adaptation because of the desensitization. This phenomenon is called desensitization. It will decrease the frequency of the action potential. The receptors can be classified based on this. The rapidly adapting of the basic receptors or slowly adapting the tonic receptors. Already we have discussed this in the previous level. The measles and the presenting corpuscles are the examples for the rapidly adapting. The mechanisms and the rufins are the slowly adapting. The other examples for the slowly adapting are the muscle spinning are the motor receptors are the examples for the slowly adapting receptors. Suppose if you look at it in this graph, the giant capsules and the muscle spinning are the slowly. The presenting corpuscles are very fast and then followed by the hair cells. Then the adaptation, the longest measured time for almost complete adaptation for a mechanical receptor takes up to the 2 days, which is the adaptation time for many of the carotid and the aortic receptors. For the non-mechanical receptors, the chemoreceptors, the pain receptors, probably they never adapted. This will save the from the so many complications. Then what are the different law of specific energies and the Mullen's doctrine of the specific energies. Whenever there is a nerve pathway from a particular sense organ is stimulated, the sensation evoked is the term for the receptor that is which is specialized. There is no matter how where and along the activity it is initiated. It is called as the law of the specific nerve energies. Last, for example, if a sensory nerve from a pacemaker corpuscle in the hand is stimulated by pressure at the elbow or by the irritation of the any tumor in the brachial position, it will produce only touch sensation only. Then law of projection. No matter where the particular sensory pathway is stimulated in the course of the cortex, the conscious sensation will be produced in difference to the refer to the location of the receptor. Suppose it is from the hand to the sensory cortex, during the pathway, whenever there is a stimulation occurs, but it perceives as stimulated at the hand only. This is called as the law of projection. For example, when a cortical receiving area of the impulse from the left hand is stimulated, the patient reports the sensory from the left hand, it is not in the head. Okay. The properties that include the sensitivity, the projection, and the graded response and the adaptability. Class
Touch receptors in the skin provide us with tactile information about qualities like the position, shape, texture, pressure, and movement of things we come in contact with. They are often classified as either rapidly adapting or slowly adapting. Rapidly adapting receptors are activated when a stimulus is first encountered, but fall silent if the stimulus remains present. They are important for detecting things like movement. Slowly adapting receptors keep responding to a continuously present stimulus and are important for detecting things like the size and shape of objects. Touch receptors also vary in the size of their receptive field, or the area they can detect signals from. Having many smaller receptive fields typically allows for better tactile discrimination than fewer large receptive fields. There are four main types of touch receptors found in hairless skin, like that of the hand. Merkel's discs are slowly adapting receptors that have very small receptive fields and high spatial resolution. They are especially dense in the fingertips and are best suited for processing information about shape and texture. Meissner's corpuscles are rapidly adapting receptors. They have relatively small receptive fields, but their spatial resolution is inferior to that of Merkel's discs. They are especially effective at transmitting information about movement between the skin and another surface. This can be used to sense texture and to detect if an object is sliding past the skin, which is important for maintaining grip. Pacinian corpuscles are rapidly adapting receptors with very large receptive fields. They are thought to be most effective at transmitting information about vibrations objects cause when they are contacted or grasped by the hand. This information may be important for the use of tools. Ruffini's endings are slowly adapting receptors with large receptive fields. They are poorly understood but seem to respond most to skin stretching, like what would occur with the movement of the fingers. This information might be especially important in generating awareness of finger and hand position.
system, basically nerve signals are action potentials. So basically all the nerves are sitting at negative 70 millivolts. Anything that pushes it towards that can cause an action potential. Action potential goes up, we have an undershoot, and eventually goes back to negative 70. Now what's causing that is going to be sodium and potassium ion flow. But basically what it looks like to the brain is an action potential and another action potential and another action potential, and another action potential. And all the action potentials are identical in size and identical in shape. But your brain is receiving those, and it can tell what the signal is based on where the signal's coming from, what nerves it's coming from, and basically the number of action potentials you get. And so if I were to make a noise like, ooh, then you'd be getting action potentials from your ear. And a set number of action potentials because it's not really loud and it's a specific pitch. But if I were to make a slightly louder noise, whoa, like that, then that's going to be way more action potentials. The first sound we could think of as like this, but the second one, it's going to be way more action potentials. They're always the same size, but more action potentials in a given period of time. And so again, the action potentials from your nose and the action potentials from your eyes and your ears and all of those are exactly the same. They look exactly the same. You either have more of them or less of them. And so you might think to yourself, well, how many senses do you have? Most people would say 5. We have 5 senses, and then we have a 6th sense, which is not something that I'm even going to talk about. But basically, that would be way underestimating the number of senses. Because you can see, you can hear, you can taste, you can smell, you can touch, but you also have a sense of balance. You make sure that you're remaining upright. You can sense temperature. You can sense pain. You can sense acceleration. You have kinesthetic sense. I mean, take your finger. Close your eyes. Can you get your finger to your nose? Yeah. How are you doing that? Well, that's kinesthetics. And then you have dozens of other senses inside our body, internal senses. And so if somebody says, we've got 5 senses, I know I'm being picky here, but we have way more. We have about 25 senses. Today, what am I going to talk about? Well, I just want to talk about 3 of those. I'm going to start with the smell. Smell's not super important in us, but it is important. But just as an example for the next 2, which are going to be vision and then hearing. And so basically, how does smell work? Well, this is your nose right here. So you have this olfactory bulb, which is right up at the top. So we've kind of zoomed into it here. And so if you want to smell something, how does that work? Well, if you really want to smell a rose, then you kind of sniff because you want to bring those chemicals up into your nose because this is a chemical sensor. Just like your taste buds are sensing chemicals that end up on your taste buds, your sense of smell is the same way. So the more of those you can get up to this point, the better our sense of smell is. And a dog is going to have way more receptors than we do. But basically what happens is those odors are eventually going to dock with these olfactory neurons right here in your nose. And every time they interact, they're going to cause interactions. And so the more interactions there are, the more action potentials are going to be sent to your brain. And your brain is going to sense that, and they're going to be able to tell you what that smell is, or more of that smell. Now, if you've ever walked into somebody's house, you'll notice that their house smells different than your house. They have a smelly house. But then the longer you're there, eventually you're going to ignore that. And so even though those smells are present, our brain can decide what we want to do with that as well. But what's going to your brain? Again, it's just action potentials that are being sent down the neurons that go into your brain. And if those action potentials aren't present, then you're not going to be able to smell it. But you're sensing a chemical smell. Let's go to the next one, which is vision. How does vision work? Well, vision, basically you have a pupil up here, you have an opening, we have a lens that we can change the focus of. But let's see if I were to draw something out here. Let's say you're looking at a person that's far away. Basically that light is going to be bent. So it's going to be bent like that. And it's going to be projected on the back of your eye. And so again, if it's that's a really bad drawing, but basically we can regulate the amount of light that gets in, but this ends up on the back of our eye. We're then going to transfer that into action potentials that go to your brain. So your brain is going to flip that image right side up. But how does that work? How do we sense that on the back of our eye? Well, basically on the back of our eye, you learn this as a kid, we have rods and cones. And so rods and cones are going to be found here. Cones will be closer to the middle because cones are good at sensing. We have what are called this fovea, where there's this area where you have lots of cones, we can sense lots of color. And then as we move farther out, we're going to have rods, which are going to sense low light conditions, but they're going to be in black and white. But what do these receptors look like? Well, this is one right here. This would be a rod right here. Rod's going to pick up light. So basically down here, it's just like a neuron, but we've got a sensory portion to it. You can see that there's a synapse here, and then that's going to send that to cells that'll go through the optic nerve and eventually to the brain. If we zoom in right here to this area, we get a lipid bilayer, and then we have a chemical called rhodopsin. Rhodopsin is going to pick up light, and so when light hits that, so when light hits rhodopsin, what's going to happen is it's going to have a conformational change in the protein. The protein will actually change shape. The rhodopsin is going to change its conformation. When it changes its shape, that's going to send an action potential down here. It's going to send an action potential down a nerve, and it's going to eventually go to your brain. And so when you see light, so if we see light here, more light on this side of the retina, that means more of the rhodopsin is changing its shape, and we're sending more of a signal. Likewise, if we see a dark area, or even if we were to close our eyes, we're going to have all that rhodopsin go back to a specific conformation. We're not going to send action potentials to the brain. You've noticed this sometimes. You're in a theater, it's really, really dark. You forget that you're in a theater during the day. You go outside, bam, and you get that light. Well, that's basically all of the rhodopsin and all the rods that are being bleached, we call that. They're sending a bunch of action potentials right to your brain. And so that's the way vision works. And vision is super important in us. And so we have tons and tons of receptors, tons and tons of these neurons that are going to send information back to the brain because we're visual kind of people. Hearing is another one. Hearing is not using electromagnetic radiation. Hearing is actually using compressional sound waves that are passed in through the air. And so basically when I talk right now, I'm vibrating the air, and that vibrated air is moving into your ear. It's going to vibrate this. This is called your eardrum. We have a series of bones which are going to mechanically amplify that until it eventually gets right here, and this is going to be your oval window. So the oval window sits right here on your cochlea. The cochlea looks kind of like a snail, and that's where you sense hearing. On top of that, we have these semicircular canals. Those are actually going to give you a sense of balance. And so there's fluid inside here, and they've got 3 different dimensions. And so basically you can sense movement through 3-dimensional space. But how do we sense sound? Well, this is awful drawing here, but basically if I were to take the cochlea and unwind it, what you get is this long tube. And so basically the fluid in here is going to vibrate. There are going to be nerves that go out of here to the auditory nerve. So again, I've unwound the cochlea. So basically what happens is you're going to vibrate the fluid inside the cochlea. And depending on the pitch, you're going to vibrate it in a different area. Example, a whale's cochlea is going to be really, really big, and so it's going to be able to sense really low frequency sounds that we couldn't even pick up. If we had something like a dog that can hear high frequency sounds, it just means that their cochlea is going to have more neurons, and it's going to have a smaller area in there. Because when we vibrate the sound, we're going to vibrate a specific portion of that cochlea, and that's going to send a signal down to our brain. Again, we're going to sense it. It's just going to be action potentials coming to the brain, but since it's going to that portion of the brain where we sense hearing, we're going to hear that as a sound. And sometimes those get crossed. You'll have people that can actually, they'll hear sounds and it'll be like a color, or they'll smell something and they'll see a color. And so it's basically action potentials going to the wrong part of your brain.
That sensation. It's reason.
Is the process that occurs in the retina, where light is converted into electrical signals that can be understood by the nervous system. It primarily takes place in photoreceptor cells, of which there are 2 main types, rods and cones. I will discuss phototransduction in rods, although the process is similar in cones. In the dark, positively charged sodium ions flow into rod cells through ion channels that are activated by a substance called cyclic guanosine monophosphate, or CGMP. This influx of positively charged ions causes cells to remain in a depolarized state, leading to the continuous release of the neurotransmitter glutamate. Inside the rod cell, there is a substance called rhodopsin, which is made up of a protein called opsin and a molecule called retinal, which is capable of absorbing light. When retinal absorbs light, its configuration changes, an event that prompts opsin to activate a protein called transducin. Transducin activates a type of enzyme known as a phosphodiesterase, which begins breaking down cGMP. As cGMP levels fall, the ion channels that are opened by cGMP begin to close. Thus, less sodium enters the cell, and the cell becomes hyperpolarized due to potassium ions that regularly leave the cell. Consequently, glutamate release decreases. Strangely enough, this decrease in neurotransmitter release acts as a signal that a light stimulus is present. The rod cell returns to its normal state quickly when activated rhodopsin is inactivated, and a protein called arrestin subsequently binds to it. Arrestin blocks the ability of rhodopsin to activate transducin, which makes the cascade unable to continue. A complex process then restores retinal to its original configuration, making it ready to absorb light once again.
Yes, so we go through the summary of all the schematics in. Suppose we look at the receptors, the tactile receptors of these particles, they are present in the capsule and the diagonal of the skin. They are carrying sensation of touch, pressure, and they are rapidly enacting. The head fluxes, the free nerve endings are wrapped around the head particles in the skin to carry the sensation of touch. They are also rapidly enacting. The vertical disc, they are propagated in the conduct and they carry the sensation of the touch and the pressure. They are slowly adapting. And the root trees are running, they are elongated in the capsules around the membrane in the center, segments and the tendons. They carry the sensation of the stretching of the skin. They are slowly drafting. Then preceding curve, the overlaying layer and the capsules around the membrane, the dermis and the subcutaneous layer of they carry the sensation of the pressure and the constant pressure. Along with this, they carry they are the rapid response. Then the ancient receptors, the period the both slowly and rapidly adapting. The local receptors of the long and the receptor, the three nerve and they just carry the long and the cold. They initially rapidly, then slowly adapting. The nociceptors of pain for the three ending nerve endings completely each of the body except the brain, from the brain, and from the floor adapting. When it comes to the proprioceptors, the neurotransmitter the joint kind of receptor. The sensory nerve endings of the muscle with the pregnancy, the nerve large around the central area of the encapsulated transfusion by the muscles, the motherland, and the slowly adapting. The tendon organs, the capsules of the enclosure of the fibers from the tendon and muscles. There is the muscle tension. They are also slowly adapting. The joint kinetic the pain and present structures and the structure and the tendon organs and the pain and the receptor structure. They the joint pain and the movement. They are also rapidly adapting. This will end today's session.